what I want to do in the rest of the time is rather to look at, to sketch what you do if you go for a second derivative. Because polarizabilities and shieldings and spin-spin coupling constants are defined as second derivatives. So what I have to do then, I have to sort of go back to this equation, where I sort of had written the first derivative, but I did not yet evaluate it for zero value of the perturbation. I'll go back to that, and I take now the second derivative of the energy and do sort of the diagonal second derivative. Just have one perturbation to make it a bit easier, which is then a derivative of what we had here. Right, so it's the derivative, big parenthesis, of where I had here the derivative in the bra. I had my H0 lambda P1 plus lambda squared P second order, and the wave function, that still depends on lambda. Then I had this term, where I have the wave function, I have P1 plus I guess 2 times lambda, P second order, C of lambda. And the last one I said before, I can do that just with a, I guess I have this one twice. Well, that's what I said before. Where is it? Yeah, basically that's what I write down here. So now I have to take the derivative with respect to lambda of all that. Same story as before. I get twice, and now the second derivative of psi with respect to lambda here. H0 plus lambda P first order plus lambda squared P second order, psi of lambda, plus from this one, but I take now the derivative here. So I get well, still 2 derivative with respect to lambda, and now I take the derivative with respect to lambda here, so I get P first plus 2 times lambda P second, so I have lambda, and I get one where I have the derivative now also here. That was the derivative of the first, and then I'm going to get similar more terms of this one. I guess I should get a derivative in the bra, P1 plus lambda P second, C of lambda. I get a derivative here of the Hamiltonian, so I get psi of lambda P 2 times P second order, psi of lambda, and I get the one in the last one. But if I take the derivative here, that's again the same as there, so I should get a 2 also here. So I can drop this one, this plus sign.
there's a 2 missing in the second half.
Thank you. Yes. And let's step one step back. Is there something more I can do? This one and that one looks to my eye very similar, doesn't it? We should have, I can, this and this is the same, so I have this 4 times. For, again, all for real wave functions. And what I have to do now is I have to, again, insert this thing. The derivative with respect to the wave function is actually a derivative. I have to use the chain rule, so it's derivative with respect to the wave function parameters times the derivative of the wave function parameters with respect to the perturbation. And that I have to do with all those up there, which then means I get, well, I keep that up for a second. Yeah. So what do I get there? I get, from the first derivative, I get the derivative of the wave function with respect to the wave function parameters times the derivative of the wave function parameters with respect to lambda. That was the first derivative. Now I take the derivative again of that thing. Now, both of those depend on lambda. So I'm going to get one term. So this is a product. So I get one term where I take the derivative of here, and I get one term where I take the derivative there. Let's write this one first up, because that gives me then the second derivative of c with respect to lambda. And in the bra, I still have the first derivative of the wave function with respect to c. The other one, I keep that fixed, but I take the derivative there. But the derivative of this, of psi, or the derivative of lambda, is then, again, the chain rule. So I get a derivative with respect to c, which means I get the second derivative, times the derivative of the parameters with lambda, once more, which means I get them squared. And then what do I have in here? I mean, this was this thing, just so I get 0th order plus lambda, p first order plus lambda squared, p second order, and the right hand side, well, as it is, just write psi now. And also here, 0th order plus lambda, p first order plus lambda squared, p second order times psi. That was taking the derivative of that. Now the next derivative is of this one. No, sorry. The next one is this one here. I have to think about. So I have plus 4 times. They have the first derivative, so I get delta c delta lambda psi delta c. P first order plus 2 times lambda p second order times psi of lambda. And then, what do I have on here? I have one. That's 2 times. So that's, here I have the first derivative, so I get a derivative with respect to c, and then the derivative of c with respect to lambda, but I also get it here. So again I should get the derivative with respect to c to lambda squared, one from the bar, one from the cat, and then I have the derivative with respect to c, h0 plus lambda p first order plus lambda squared p second order, psi back to c. And then this one is the same with this one, so now I only have this one and there's no derivative anymore, so I get twice psi p second order psi. Okay, now what do I get? I mean, I have, what do I have here? That is the derivative of my wave function, and then the full Hamiltonian, and psi. So if I set lambda, the perturbation, to 0 eventually, what I always eventually do, this is the derivative of psi, the unperturbed Hamiltonian, and psi, and that we had discussed before up there. This is what we have up there. So this term, for a variational wave function, this is going to be 0. I have 2 minutes, so I rather have to cut it short. Now I can do the same thing if I write this variational condition up with the full perturbed Hamiltonian. One can show that those 3 terms are actually related to each other. And it is shortly discussed in the book, and unfortunately I don't have the time to do that. But you can show that, and which means that this plus that, those 2 terms, are actually minus to this term. So this one plus this one gives me minus this one, which then in the end means those and those, and there are two, and 2 of those here go away, and I'm left with just 2 of them. So I'm left with 2 times dc d lambda c first order plus 2 times lambda second order lambda plus that at the end p second order psi of lambda. And if I finally let lambda go to 0, I get that the second derivative is then 2 times the derivative of the wave function parameters with respect to lambda, the derivative of the wave function with respect to the wave function parameters, the first order operator plus 2 times the expectation value of the second order operator. For variational wave functions. For the second order energy, you need the derivative of the wave function. Now if you compare that with our perturbation theory expression which we had before, we had a ground set expectation value of P2, and we had this sum over states term. But if you think about perturbation theory, this actually corresponds to the first order wave function. So this corresponds to psi first order. And we actually have the same expression again. If we use now sort of a first order wave function being expanded, we would get the same sum over states expression again. So the trick, what happens for variational wave functions here, because you can there's that, you don't actually need for the second order energy, you don't need the second order wave function. Or you don't need the second derivative of the wave function. That is like the 2n+1 rule which we had in perturbation theory. You can get away, you can rewrite it so that you only need the first derivative of the wave function.